All right, so let's transition from those calculation-based questions now and talk about Lewis bond theory, polarity, resonance, geometry, and hybridization, which are a big part of the last unit. And then we'll talk about another theory for bonding, namely molecular orbital theory. So I want to go through some typical Lewis forms here that obey the octet rule, and also a few that either expand or lack an octet to remind you of those concepts. But if you sum up the valence electrons of POCl3, there are 21 due to the chlorines, 6 due to oxygen, and then an additional 5 due to phosphorus. So that gives us a total of 32 electrons. Phosphorus generally likes to make 3 bonds. It's the least electronegative element here and goes in the center. And each chlorine only will make 1 bond and retain 3 lone pairs. And then phosphorus is going to bind to oxygen. But oxygen generally likes to make 2 bonds such that it has 2 lone pairs and a full octet. So the best resonance form for this compound is to actually draw 5 bonds at phosphorus, or there are 10 electrons around the phosphorus atom. It has expanded the octet, but that's okay because phosphorus is in row 3, and atoms that are in row 3 and larger, phosphorus, sulfur, chlorine, and below, can undergo octet expansions, especially when they maintain a 0 formal charge. Remember, you can calculate formal charge. For phosphorus, it has 5 valence electrons, and here it's making 5 bonds, and it has 0 lone electrons, so it has 0 formal charge. It's pretty happy. The phosphorus has 4 domains around it, and so it's sp3 hybridized. And an sp3 atom generally is going to take on a tetrahedral geometry. So really, if we're drawing the correct geometry for that structure, it would look something like this, where 2 of the bonds are in the plane, and then one of the chlorines, or it could be oxygen, comes out of the plane, while another one goes back into the plane. And keep in mind some general electronegativity values. I'll sketch them up here. So phosphorus is pretty low in electronegativity. I'd say that value is probably around 2 to 2.5. And oxygen and chlorine are much more electronegative, with oxygen being the smallest and the most electronegative at 3.5, chlorine's 3.4. So those differences in electronegativity are all greater than 0.5. So these bonds are all very polar, and they point towards the more electronegative element. So the charge on oxygen and chlorine is partial negative. The electrons are polarized that way. And the phosphorus is electron deficient. And this molecule is polar overall because it does not have perfect symmetry such that those bond dipoles cancel, right? This PO bond dipole is different from the PCl one. And so they're not totally going to cancel out in space. It's a polar molecule with a permanent dipole moment. And like I said, we would mention that this geometry is tetrahedral. Okay. So let's look at another exception to the octet rule. Phosphorus is a common one, but so is boron. And boron trifluoride is going to feature a total of 24 valence electrons, 3 from boron and 21 from the fluorines. Where boron generally makes 3 bonds, fluorine makes 1, and so fluorine will have 3 lone pairs. So in other words, this boron atom with 3 domains is sp2 hybridized. And it has only 6 electrons that it's sharing, or no octet. But for group 3 metalloids and metals like boron and aluminum, it's actually okay to have no octet. The formal charge of boron is 0. It's 3 valence electrons minus 3 bonds minus 0 lone pairs. So that gives us sort of a happy boron atom that actually lacks an octet and has an empty p orbital. The geometry of this atom, sp2, is trigonal planar, so it's fine just to draw it such that all the fluorines are in the same plane. You can just draw it with flat lines. And fluorine is way more electronegative than boron. So each of these bond dipoles points towards the more electronegative atom. The fluorine is electron rich, and the boron is electron poor. But this compound is highly symmetrical. And these bond dipoles are going to cancel somewhat with each other, and they cancel with the other bond dipole to make this molecule nonpolar overall due to symmetry. So only if those bond dipoles are equal and evenly spaced apart will they cancel to give a nonpolar compound. Okay, so there are other ways you could depict this compound, but I'm going to save that argument for the following example, where we have CH2NO. So carbon is going to be the central atom. It wants to make 4 bonds. And nitrogen generally wants to make 3. Oxygen usually wants to make 2. So I'm going to connect the oxygen and the nitrogen here. And the carbon will probably have at least 1 hydrogen so that it can start working towards having 4 bonds. But the nitrogen also likely has a hydrogen bound because it likes to have 3 bonds more than oxygen. The way that we can now fix this structure and give oxygen 2 bonds along with carbon so it has 4 would be making a double bond here. Okay, so if you add up the total electrons, they're going to be 18 in the structure. 6 from oxygen, 5 from nitrogen, 2 from the hydrogens, that's 13, plus 4 from carbon, that's 17, but there's a negative charge, so that's an 18th electron. So we need to populate this with lone pairs, right? We only have a total of 5 bonds shown, or 10 electrons. And oxygen certainly wants an octet, so it needs 2 lone pairs. And the nitrogen would also like an octet, which gives it 2. Now, carbon has 4 bonds, which means that its formal charge is 0, right? It's 4 slots away from the noble gases. Oxygen, which is 2 away from noble gases, has 2 bonds, so it's also happy in 0. But nitrogen has a formal charge here that's non-zero because it's making only 2 bonds, and generally it will make 3 to be neutral. It has 5 valence electrons. It's making 2 bonds, and it has 4 lone electrons, or 2 pairs. So it has an extra lone pair compared to normal, which makes it electron rich and negatively charged. Now, you may be asking, well, aren't there other ways to depict this compound? And that would be true. In other words, this is not the only valid Lewis structure, and the true compound is more complex. So this arrow pushing you'll see later in an organic class, but I want you to notice that the nitrogen, which is electron rich, could instead share what we're showing as a lone pair with the carbon atom. And that would give the carbon a 5th bond. So simultaneously, the CO pi bond would need to break such that we push a lone pair onto oxygen. I'm showing another resonance contributor here, where we have a CO single bond. The hydrogens and the sigma bonds do not change. And there's a negative charge on the oxygen. One lone pair remains on the nitrogen. So these are two resonance forms. I'm just going to give them different letters, A and B. But now the oxygen has accepted a new lone pair. And so its formal charge is 6 valence minus 1 bond minus 6 lone electrons is -1. So each of the resonance forms has a net -1 charge. Now, when you're thinking about resonance forms, remember that it's not an equilibrium. It's not these arrows going back and forth. These are not two different molecules. These are just two different simple pictures that we can draw that describe a more complex hybrid molecule. And we're going to draw that hybrid below. Now, the hybrid may be equally represented by A and B, or one of the two may be a better or a major resonance form. So we have to diagnose which resonance form is better and why. And each of these has a negative charge, which means they all have plenty of electrons. There's more than enough to go around, or there's more than an octet. So everybody has a full octet. We're not worried about the octet rule in this example, but that's what you look for first. Here we just have one negative charge, so we want to optimize its placement. And the negative charge would rather reside, or preferentially be, on the more electronegative atom, oxygen. So this resonance structure here is slightly better than the other one, major and minor. So the real molecule looks more like B than it does like A. So the hybrid is a weighted average of those two resonance forms. And it says that there's always at least one lone pair on nitrogen, minimum. That's not delocalized, or it's owned by the nitrogen. Sometimes we show 2 lone pairs on oxygen, sometimes we show 3. So there really are just 2 that belong there. The other lone pair is delocalized or spread out in the form of a pi bond here. And there's also a pi bond that can be shown between C and N. And the oxygen takes on more negative charge than the nitrogen. So we show those partial negative charges. That's the hybrid. It says that these atoms are always pi bonding together. Okay, there's somewhere between a single and double bond between C and O, and the same thing between C and N. It's not a single, not a double, but it's an intermediate bond order between 1 and 2. So let's think about what this looks like in terms of an orbital picture. The carbon is clearly sp2 in hybridization, has 3 domains around it. If the oxygen is making a pi bond in the true structure, then it's also sp2 hybridized. Even though it looks like it's sp3, if it can make a pi bond, then it must have a p orbital, and it actually is always the same hybridization. It's not changing. It's always 1, and that's sp2. And the nitrogen is also always participating in a pi bond, or a partial pi bond. So it's also sp2 hybridized with 3 domains. So the carbon, if it's sp2, it's trigonal planar. Now I'm going to draw these 3 groups in the plane. That plane is coming perpendicular to the screen, like if your hand is stretching out this way. It's connected to C, or C is connected to N and O and H. And the H has a hydrogen on it. Excuse me, the N has a hydrogen and a lone pair. The oxygen has a couple lone pairs. And each of those atoms, because they're sp2, is going to have a p orbital. And the p orbitals are above and below the sigma bonding plane. And the number of pi electrons is 4. You can show it as a lone pair on the oxygen and a pi pair between C and N. But really, those p orbitals are all sharing pi electrons in what we call molecular orbitals. Where they're always parallel and forming those partial pi bonds. So in terms of bonds here, we can think about, of course, the first bond between each pair of nuclei is sigma bond. There are 8 sigma electrons. And then pi include this double bond here, and then the lone pair on nitrogen that can become a pi bond. There actually are 4 pi electrons. And then any lone pair that just doesn't move, meaning this lone pair and these two, those are not bonding at all. So there are 6 non-bonding electrons here in the real molecule. The non-bonding ones are not spread out over multiple nuclei. They are owned by a single nucleus. And we would say that the bond order of CO is somewhere between a single and double bond, stronger than a single and weaker than a double. And the same statement could be made about C and N. And the true hybridization is sp2, such that all of those atoms have a 2p orbital that's left unhybridized, and they can pi bond with one another. So what I'm showing here is those 4 pi electrons as a pair and then another pair in the p orbitals.